like the perfect pace for a 70-degree rainy spring day, the first week of March. I don't know what's going on. So I'm really happy to introduce Christian and Erik, who are going to talk about their Graspable Math, which I'm really interested in hearing about. So thanks so much for agreeing to come and give a talk, and looking forward to this.
Yeah.
Could you provide a little more background for those of us who don't actually know what superposition was?
Oh, would you like us to go around?
No, I just don't know who they are.
Oh, sure. Well, go ahead and introduce yourself.
Okay. Yeah, I will do that. So welcome, and thank you for inviting us here. Thank you for being here. So this is Christian Achgill. I am Erik Weitnauer. We are representing our work on Graspable Math, which is a digital algebra notation. And we've done this work in the lab of Professor David Landy in psychology, actually. So there's some cognitive science background in this. And yeah, I'll start with giving you a bit of this background information of what our motivation behind this is, why we are doing this work, and then we'll demo the system and talk a bit about what our current and next projects with it are. So algebraic notation is basically this really powerful human invention which allows us to extend our cognitive capabilities and think about things deeply which otherwise we would have a very hard time thinking about. Although, like, not always, right? So it's also can also be really hard to get, and actually, like, a lot of students in schools get a lot of frustration out of working with algebra. So we have two kind of distinct interests in dealing with this topic, and one is, as I said, comes from a cognitive science perspective, where we are interested in how does this actually work? Like, how are we capable with our cognitive systems to reason about something as seemingly abstract as algebra or mathematical content, and what role do formal notations play in that? And and the other perspective, or the other motivation we have here, is more that of an engineer or a UI designer, maybe, where we think about algebraic notation as an interface which allows us to work on and reason about mathematical content, and then we might ask the question, like, how can we improve that user interface? So let's actually do this part on the board. It's kind of cool that I have this board here. So maybe, do you want to try and put on the light a little bit? It's the leftmost. Wait, I think it's this one. So, okay, so what I want to do is actually just go through this, not very complicated algebraic problem here, and let's say we are trying to solve for x here. So just to remind everybody how we would do something like this, right? In this simple case. So in this case, one thing we might want to try first is actually, like, get rid of this fraction. So we might try to move that x over here by multiplying by it on both sides, and we'll just say, okay, it's not 0 for now. So we'll get this to the other side, and then there's also this 2 we might want to move inside these brackets, like distributed here. And if we do both of these things, we might arrive at something which looks like this here. Okay, and so now the next thing we might notice here is that, oh, actually these two things here are identical. They are on the opposite sides of the equation, so we can kind of get rid of this, get to this state here. And now finally all which is left to do is, like, bring the 2 over here, maybe swap the sides to have our x here, and we'll get to the solution. And so what I want to draw your attention towards with this is that the way I described this and worked through this actually was pretty spatial. So I used a lot of very concrete spatial descriptions or gestures to get here. So it was something like, move that over here, or combine this, or bring this to the other side. And that's, like, when we stop and think about it, I mean, that's not something which is necessarily inherent in the mathematics, right? In a way, it's just scribbles I put here, and then there are some axioms which allow us to write some more scribbles over here. But it actually turns out that the way we're doing math seems to be very spatial, very concrete in a sense, almost like treating these symbols we have here as objects. There's a good amount of research on this by ourselves and by others, which actually looks at that people do use these notions and use their perceptual apparatus, their visual apparatus, and also their motor system to help them perform these transformations to go through these algebraic steps like these here. And right, so maybe one more slide. So so the view we have in our lab is from these observations we made is that what kind of happens is that a mathematical reasoner co-opts their visual motor systems which they have to help them do the hard algebra work on these notations. And in a sense, these notations are optimized maybe through history to allow these kind of things. This is at least one possibility here, right? And so what in this view this notation does is it actually turns a task which is pretty hard for humans per se, this kind of abstract rules which you have to apply in a long sequence, and turns it into tasks which come more natural to our cognitive capabilities. Turns it into tasks which involve visual pattern recognition, thinking about dynamics of objects, and maybe interacting with objects. Okay. So let's look at the UI design side for a while. So this is kind of our background on the cognitive science side, and that informs like our intuitions of how to maybe build a slightly better interface for doing algebra. And on this side, so we are not going to look so much actually or at all at how we might like reinvent the notation itself to write things differently. This is something which happened throughout the history quite a bit. But for now, in our work, we'll actually look at how it is that we can use this existing notation in a more efficient way. And so one thing which is maybe a little surprising about the way we use this notation is that manual writing is very popular in math, actually. Like we have computers and all these things, but you see a lot of chalkboards, whiteboards, pen and paper in use, both when people learn mathematics, but also when like professional mathematicians think about new things, trying to gain new insight. Okay. And part of the there's some really good reasons for this that people have looked into. So people say that they use this kind of mode to interact with this notation because, well, it's very flexible, right? You can write whatever you want. It's also very clear. It allows you to be very deliberate about which steps you explore next, and so on. It's all things So there's, of course, this important place for computer algebra systems which we have, which can solve things automatically. But this is still something which is really, really important in this process of exploring new things and gaining new insights. So, okay, so just to build some intuitions of like, okay, so these are good things about papers, but there are also some ways in which paper really might limit our mathematical reasoning or how we can think and work and learn algebra. And I really like this metaphor, this analogy here, which is kind of it's this thought experiment where we imagine, like, let's say we know some rules about chess, and now we're trying to learn chess in we're trying to use to learn chess using a pen and paper way. Okay, I'll actually, so let's say, so maybe I would start a chess game by drawing out a board on pen and paper, right? And then I do a move and I have to draw the whole board again. And I do another move, I draw the whole board again, and so on, going through my game. And I'll actually, like, a big chunk of the time, I'm just copying pretty exactly what was in the previous step, making small adjustments. And the problem with that is, if I always do it like this, I mean, it might sometimes be kind of nice to do this to really get down to the details and so on, but like, for most of the time, this will just be a slow and distracting process, right? Most of the time, I might be busy a lot of times just copying things over, transcribing things, which is not really about what chess is about at all. It's also kind of error prone. Like, even while writing this for this, right, I made a couple of mistakes. You can just easily forget symbols here or put in additional symbols and so on. And it's also kind of hard to follow when you see somebody doing it, because like action is all over the place. I'm writing this whole thing, and it's not so much focused on the areas where actual change is happening. So of course we know there's a different way to do chess, right? We can use chessboards, physical or virtual chessboards, and it makes making moves faster. It might help focusing more on the things which chess is about, like the strategy of the game and so on. And while you can still make a lot of strategic errors in how you play, it prevents you from doing the more meaningless errors. For example, just like forgetting to copy over one of the pawns while you were copying your chessboard with pen and paper. So of course, back to algebra, we are using pen and paper a lot, and there are some good reasons, but there are also these same costs, I would argue, to a certain degree, as we have in chess. When we copy these lines one by one, so if we are trying to quickly explore things and maybe have expressions which are a bit more complicated, it takes time to write these things. While you watch it, I write all over the place instead of just working on the things which I actually are trying to manipulate. And there are a lot of mistakes I can build into this while I do this, which don't really have to do with the actual math I'm doing. It's just like, oh, I didn't transcribe it correctly. And these kind of problems are especially big for kids learning this, because this exact transcribing, that's actually a whole set of skills which you have to be really, really good at before going through something like this. Like, you can even start going through something like this by yourself on pen and paper. Okay, so so for chess, there's this different way of doing it, and then maybe for algebra there's two, right? So this is just like some intuition of like how we think about this, so we would like to extend like the algebraic notation like we have it, but present it in a different way that adds like makes it more efficient to use, gives people more feedback, makes it actually explorable, and helps focus on connections, the dynamics, and the strategic of solving problems like this. So actually, like, these two interests led us towards the same kind of project, which is building and testing digital algebra notations. And it's kind of nice how these things work together in my mind, as like, of course we'll get like inspirations from our experiments here towards what a good design might look like. But then also, by actually building it, we can get a lot of data, and we can put theories on this side to hard tests. Okay, so our latest and by far so far most powerful implementation of such a digital algebra notation is called Graspable Math, and so these are the people involved in this. So David Landy, Robert Goldstone, Aaron Ortmar, myself, and David Prokop, Christian here, and Thad Martins are people who were really the people who put this together.
What's the time scale? When did this started in 2007 or earlier than that?
Right. So David Landy has been working on these kind of ideas for probably 8 years. And this Graspable Math system has, so we worked on this for, I think, 2.5 years now.
So if you started doing it in 2006, 2007, and this particular piece of the project is like
2013, right. Mm-hmm. So it has some predecessors too. Okay, so this was kind of the first part of the talk. We'll switch to actually looking at the system, showing some demos next, and yeah. Should I do this part, or do you just want to take over and go through this one? Yeah.
Yeah. So when we said digital notation system, of course, you know, we can describe it and use words as much as we want. So we can describe this with words as much as we want, but for most people it doesn't really make sense about what this is and what it actually does until we actually start doing something with it. So this is actually a tool. This is our main tool, basically, that we have. This is actually live off our webpage, so you could go and access the URL that we're at here and start using this yourself at any time. And the analogy we have here, the reason we have this big white space is because this is supposed to be our implementation of a whiteboard. So this is the surface that we interact with things on. And we have some toolbars up at the top. You can probably figure out what most of the, well, not all of them, but most of them, we have basic functionality, like the functionality that you get with a traditional whiteboard. But when the digital notation comes into play when we start creating some expressions. So I'll use the same one that Erik had on the board over here. So we have So this is that same expression put on our whiteboard. And so the way that we interact with these kinds of things is that we use gestures. So we can either use gestures that are controlled by the mouse, so using the clicking and holding and stuff like that and dragging, or we can use it on a touch interface, so on an iPad. We also have our tapping and dragging and stuff like that. And so, for instance, the first step that Erik did was he pulled this, he multiplied both sides by x, but when he talked about it in physical terms, we could say that we're pulling this x out and bringing it to the other side. And so I can actually use the mouse to click and hold on the x here, start dragging, and I can pull this out and put it on the other side of this expression. And then I can do things like pull it into these parentheses here. I can turn these two x's into x squared. And likewise, I can pull the 2 in here. And if I need more space, I can hide some of these steps that I've done. I can pull more than one thing off at once by using our rubber band selection tool here. I can bring this to the other side, cancel that out, add these two numbers together, and then if I want to get x, I pull this out over here, and then I have the same solution that Erik arrived at on the board. So this is kind of a lot of where our work goes into, is mapping what are the right kinds of gestures to use to perform the right kinds of operations. But that's of course not the only thing that we do. We also, when we were working with, when we're addressing different types of problems, maybe it's not always the case that using pure algebra is the best way that we want to think about a problem, because everything that we're doing is kind of addressing how do we better reason about the types of problems that we're trying to solve. So we do also have some additional tools here. And this. So we also have an implementation of a graphing interface. And with this tool, we can create lines. Right now, within the graphing interface, we mostly focus on linear lines, but we also can put some nonlinear lines into the graph. So I'll start by making some lines here. And of course, we can kind of control these using gestures like we did with the mathematical expression. So I can change the slope of this line. I can change the intercept. And if I create two lines, we're going to show some additional capabilities that we have here. So the other thing that we can do, and this is pretty powerful, is that we can link different representations together. So we could represent a line either as an expression, of course, or we can represent it as the actual physical drawing of a line on our graph. And so when we have these alternate expressions, we can easily move between them. So I can pull this equation of a line out, and these are still linked together. So if I make a change to one of these things, like if I change the slope of this line here, then the expression will update. And this linking tool is actually, we can really do some pretty powerful stuff with it. So for instance, if I want to find the average of these two lines here, I can basically just keep adding additional layers of linking. So if I create a new expression, I say y equals y plus y over 2. What we can do with any expression is we can substitute variables, and then whenever we make a change to the original variable, then that will propagate through any other linked representation. So here I'm going to average these two lines out by putting one of these expressions into one of my y's and the other expression into the other y. And then I just have to break this down. Give myself some more space here. And break this off. Break this x off. And then I can put this into my graph. And so if I made any change to the line that I just created, nothing would happen to the other lines because that wouldn't make a whole lot of sense. You can't really go back. Since this is the average of these two, what exactly would I do if I tried to change the average line? But if I take my original lines, these are still linked, and so then any change to one of these lines will update the average line. And so we can also do things like we can get the point of intersection here. So what I could do is I could solve this system of equations here. I could link these two representations together and solve for x here. And I'll move this out of the way. Pull this over. And then I could put this x back in. Sorry, we don't have a lot of space on these screens here. And then if I create the representation of a point, I can again substitute. I can put this point back in here. And we have this little point right here. And again, any changes will be propagated throughout the entire system. So we can do some pretty advanced stuff with it. But there's also, one of the reasons that we started branching out into things like different representations like the graphs here is because we do also want to apply Graspable Math to domains that rely on math, but where they're not really focused on the pure algebra. So in physics, of course, whenever you open a physics textbook, you have all these sorts of diagrams that where they're tying in variables to maybe if you have something on a ramp, you're going to have some friction coefficient, you're going to have gravity acting on things, and so this is one of our sort of future areas of research. How do we tie this into other domains? And we also, in making things accessible and making things easy to use, we also have a tool where this is a Chrome plugin, and what it does is it allows you to pull in mathematical expressions in other basically documents and get the same power that you get from Graspable Math. So here I have this Wikipedia article, so if you were going through this and you saw something that you thought was kind of confusing, that you wanted to understand better, with this sidebar, what I can actually do is I can pick up this expression here, drag it in. If I wanted to say, okay, I don't get how this thing over here is the same as what I just saw, then I can, of course, start trying to get this into the right form. And so with this tool, then we can start working in other domains and applying the same sort of ability to reason about the problem. No.
It is an image. We don't do image recognition though. It's just like they are nice enough to have an alt tag, which is actually the LaTeX formula.
Yeah.
So that's how that works here. Yeah, there's some hidden LaTeX there which we can parse. So we can parse LaTeX and kind of an ASCII representation of these things too. So basically, this is one of the things I'm most excited about, right? To take this dynamic algebra where you can actually interact with it and make it work together with all the things which are already out there and working. And in this example, you could also imagine this actually replacing the expressions themselves in place in this page, right? They would even look cooler, but then I don't know, kind of, then we change it and it says something wrong, I know. But so connecting these things together is, I think, really exciting. And we have, we are at a point where this is not that hard to do. So there's, I don't know if you ever heard of GeoGebra or Desmos, these kind of tools, and these are tools which really focus on being on being very powerful graphing calculators in a way. And
you want to do this?
So we got this working here. So I just recently tried this out and did this. So this took like a day to do. So over here is this Desmos interface. And it's actually it's a real cool and powerful project, which is used a lot in schools and so on. And and right next to us there sits our Graspable Math canvas here now. And I have it hooked up so that it actually like listens for changes over here, and if I change this, it changes these things here. And this is just a list, but I can again pull this in here, okay, and create a new expression here where let's say C equals A plus B, right? Pull this in. Oh my God, we don't have a mouse. How did you? Wow, I'm impressed. Like, how did you manage to do this so well? Okay, so I'll just add these 2 points. So now it's kind of adding these 2 vectors, right? And lets me pull it back in here, and now it adds it actually to the GeoGebra side, right? So if I now move this, everything in here will update. So what we did here, and it was rather easy to set this up, I have to say, is like allow to pull objects in this geometry domain here, put them over here, do something, and put the result back over here. That's just, like, in my mind, a really powerful way of, like, having this new way, a new view of exploring relationships and things in there. And it's kind of nicely complements, maybe, because each of these has different affordances and different good things about it.
And so, of course, Graspable Math is something that we want to bring into the classroom. And as we found early on when we were, making efforts to do this, that one of the things that teachers really wanted was not just something for the students, but something for themselves as well. And so we thought, okay, well, we're really focused on this. How do we make things easy to reason about? How do we make things easy to access? And so I'll just write something on the board real quick because we don't have the demo up and running. But so now what we're also focusing on is if we give this tool to the students, we give this tool to the teachers, Of course, they could use it to teach lessons during class, but they could also use it for homework purposes. And so, of course, we want this interface where a teacher can say, I want my student to work on this number of problems, and I have 30 students, and then after they've done all this work, I want a way to really see how did the class do as a whole, how did each individual student do. And so one of the tools that we developed recently was this basically visualizer. So if I give a student a problem like 2y equals 4x plus 12, then it puts it into this sort of giant graph type view where everything that a student did, every time they sort of took a new step and got the expression into a new state, we have a node here in this tree that represents one of these. So we have one per state that a student could have visited. So we might have y equals 4x plus 12 times 1/2. So some students may have grabbed that 2 and pulled it over here and kept it as a fraction. And so then they might have rearranged something over here, but then from here, there are some students who would say, I'm going to take this fraction, I'm going to directly bring it into these parentheses here. So you might have some that get to y equals 4x times 1/2 plus 12 times 1/2, but then there are other students who, of course, would say, well, I don't like working in fractions, so the next thing I'm going to do is convert this into a decimal. And so basically, we just have this giant representation of all the things, basically the entire set of students who were given the problem did. And so that kind of gives you a way to see what was the most, what was the, where did students really have a lot of creativity? Where do they really diverge in the ways that they solve the problem? If it's a very narrow tree, then maybe the students all did something very similar. Maybe some students took a really long time to solve the problem. Maybe some students solved it really quickly. But then another thing that we realized based on the sort of internal so that's basically what it looks like. One thing that we realized based on the internal representations that we had in our system that...
Wait, before you jump to the model, can I add one thing about this? The Christian just said, we built it. I mean, so yeah, we have this visualization, but actually this is kind of one of the big challenges which still lies ahead. Because you can imagine if you had like 100 students doing this or something, and everybody might do about the same thing, but just slightly different things. Maybe one starts over here, over here, over here. Get this huge graph of paths to this, and it kind of immediately gets impossible to read and to get something useful. So this is something where we actually would need to summarize, to somehow intelligently extract strategies or common paths across similar but not identical places in this problem space. And so that's something we are currently working on and brainstorming on, and I would say we're just at the very beginning of turning it into something useful. And it could be really useful for teachers, of course, looking at what the class does and where it fails and so on. And equally exciting just for researchers, right? Having ways to coming up with good ways of analyzing this data. And this is also one thing which is kind of new with Graspable Math, something which might not have been out there before like that as soon as we get more people using this, we'll have this massive amount of data of people actually going step by step through these problems. And I imagine there are a lot of interesting things people can look for in this ability.
Yeah, and so one thing that we noticed, one thing that we needed to do for the teachers was that we needed to give them a way to create all these problems really quickly and assign them as homework. One of the things that we wanted to do was to say we have this problem generator, so we can say, give me a type of problem and then randomly create a bunch of problems per individual student. And we can do that with the representation we have, so we can easily swap out if we have a variable, we can swap it out for any other variable or numbers, or we can, if we are adding a number, we could swap that out for not just a number, but an entire sub-expression. And so one of the things that we needed was, a way to verify that the problems that we are creating are actually, solvable, and that they're solvable for the particular set of students you have. So you may generate a problem that just your students are not at the level where they can do that. And the other thing that we have is when we have this tree, or this graph of things we can do, it also allows us to do things like, if you see that your students are really struggling with one particular concept, we also have tools that allow you to do things like, you can mark a particular state so that when a student arrives at that state and the problem, you can have a message pop up that says, we didn't get to this in class today, but here's what you should do from here on out, or the reason I think that you made this mistake was because, et cetera, et cetera. But also what we'd like to be able to do is to say when a teacher is about to give out the homework assignment, so before any of the students have actually worked on it, can we sort of predict how the students are actually going to behave when they see these new problems? So could we generate an entire graph before the students even see the problems based on how they've performed the homework before? And so one of the things that we're working on now is given any expression, we can get all of the sort of actions that we can apply from that expression. And so then when we apply those expressions, of course, we get a new state, and then we can get the actions we can take from there. So this is just a random action taker. So every second, it basically just goes over all the actions it can do, and then just picks one at random, and then applies it. And the goal is to get from the initial state to the end state. And so it'll do some pretty dumb stuff sometimes. So it can take a really long time to get there. But so now one of our projects is to say, once we have this enormous set of data from our students, is there some smart way that we can start building models that actually learn when a student is given a particular type of problem or a sub-problem or something like that, can we pick the action that they are most likely to do? Because then if we do that, if we can generate these giant graphs that are sort of simulations of the way that an entire classroom would solve a particular problem, then a teacher, before you even give this out, before you even run into any problems, you can kind of say, okay, maybe I didn't cover something very well in class today because my model or my simulation is always failing at this particular step, so that might mean that my students are going to run into the same problems. So this is kind of us getting into some more really intelligent agent type stuff. Of course, this isn't intelligent. This is just, as you can see, it's taking a really long time to do something really simple. But kind of the reason that we're getting into this area is just, how can we use these really predictive, powerful tools to kind of gauge a student's progress, help them along, pick the right time to help them out, pick the right types of problems that are best for them, and those kinds of things. I think we're back on to the slides now.
Okay, so I could talk a little more about some of the things we are planning to do in the near future on this. So I don't know, maybe people are also interested in kind of the software architecture and what kind of development process we use to do this. Or I mean, I'll be happy to just talk about this a bit and hear your questions. So, do you have any questions on that?
There are many ways to try to do things in the
Like when it comes to what kind of actions we
you also have to have an iOS and Android version.
Well, so this runs in the browser. So as long as we do have sometimes if a new tablet device comes along, we run some issues with that particular browser. But like this runs in Chrome on the iPad or in Safari on the iPad.
Oh, okay. You don't have a native iOS.
No.
Some of our previous software iterations do, but this particular, it just runs in the browser and then it picks up the touch actions.
I've had people try to do that to me and fail. But just quickly, how do you succeed to get it to run in multiple browsers?
So that might just be like a couple of, I don't know when they tried, but if it was a couple of years back, then it was much, much harder at that time. So browser technology advanced really quickly recently.
Even recently, people have trouble getting JavaScript across platforms.
And we do well. So we do have some trouble too, of course, and we don't very well support Internet Explorer, and we even have some problems with Firefox. Yeah, so we run into similar problems. But I mean, there's also this big benefit that it just works out of the box. Like you just go to a web page on whatever device you are on, and
Right. I've tried that, and it's not easy. I'm just curious, can you just, like, 5 minutes say what techniques, what strategies you choose?
right. So we are using JavaScript. We're trying to use JavaScript for everything we are doing, right? And that's not just on the client side. That's also on the server side. You can now use Node.js to do and write all the server-side logic in JavaScript. Although we didn't show much of that yet. I mean, a little bit on this where we actually have to save and collect this data on the server side, right?
I mean, are there outside packages that you use, or you built your own? Or
So
what's your support structure?
right. So we are basically using like just what HTML, CSS, and SVG, scalable vector graphics, is what we are using here for most of this graphics and animations. And we're using mainly one big library which is called B3, and it's by Mike Bostock. It's a fantastic library in my opinion, and it's very powerful for doing data visualization and binding data which you have to visualizations on there. So we don't use that much of it actually, but we use it for doing these nice kind of animations. And on the CSS, on the styling side, we use the Twitter Bootstrap styles, but that's basically it. We did a whole lot of software developing for this, and really like the biggest part of the code is the one where we define these kind of interactions, like what kind of gestures you're allowed to do and how this translates to mathematical transformations. And then like technology-wise, we try to do this, and I think that's really important. We try to do this in many small iterations. So we basically every 2 weeks we set goals, and we use. Well, you can show this. We use so it's on one of the slides here, and then we use Trello, which is a free tool to like. So this is, for example, this is called Scrum. So we use some version of the Scrum process, which basically means like these short iterations that kind of have some roles in the process. So here that's our current sprint actually, and then we come up with a number of goals we have. We put these on these kind of cards here, and then we just like people take on these tasks, put them in progress, then we do all this on GitHub with Git repository, and people make pull requests, we merge this in, and then it's done. At the end of the sprint, it gets deployed to the web page, and that process has worked pretty well for us.
Something just to touch on about your question about the iPad and everything. So some things that we did have to do, so it depends on the issue. Like for us to get the touch working just like we get, to get the touch working just like we get the mouse working on the desktop, we do have to have like this custom library that sort of picks up on this iPad specific interactions and sort of remaps them. So the way that a hold works on the iPad, so we have the mTouch library. Some of those things are trivial. Sometimes it just depends. Like so, sometimes in iPad Safari, certain calls in JavaScript just don't work very well, and so you may just have to identify that that's what the issue is, and then when you know that the device it's running on is the iPad, you just have to write your own version of that function call or use some other option or whatever the alternative is. So a lot of it is unfortunately just trial and error and then exception handling, depending on the device.
You said there was an iPad touch enhancement library that you used to.
Oh, well, that's actually some little code which I wrote, and it's really helpful to have some abstraction to handle like the mouse events and the touch events in one general way without having to. And I just wrote this little abstraction layer to do this. But overall, I would say we don't spend that that's also because we didn't care too much about this yet. So if we push forward bringing this out as a product for schools and so on, that might change a lot.
Let's talk about Microsoft released last year. Microsoft released a tool to convert every thing to iOS, Android, and Windows Phone. And the language is just HTML and JavaScript. It is called Apache Cordova. That it brings Apache in your whatever Android, iOS, and Windows Phone, and runs HTML and CSS and JavaScript. I think it's the best tool for converting all of your work to native to just iOS and Android and Windows Phone. That you can easily convert it. Apache Cordova.
Apache
Cordova. It is included in the new Visual Studio of Microsoft. It is great. I have used it. Secondly, I have a question. Because I was a teacher in my country, before I came to the United States, I was a teacher, high school teacher for 8 years. And
Which subject?
There were a lot of tools that students got used to solve my questions and copy and paste for the assignment. For example, there were GeoGebra was great, and that I used in classroom for example the parabola thing, and the tools, other tools, I think Algebrator and Wolfram Alpha that solve the equations. They all solve all the equations. For example, algebraic equations. So I don't understand that. What do you do in additional to these tools? What your tool do? What your tool does that these tools doesn't? These tools, for example, Algebrator and Wolfram Alpha and GeoGebra doesn't.
So I don't know Algebrator, but I know the other tools, and they're actually a lot more like computer algebra systems out there, of course. And when it comes to like using them for solving an equation, the thing that they all seem to do is you type in the equation, then a command or hit the solve button, and it actually does all the thing for you. And then you can come in and maybe look at the steps. But the big difference here is that you're actually still in control. You're actually triggering each single step you're doing yourself.
So we are doing, not the computer. Yeah, we
Right.
are doing
The users are doing this. The students are doing this. So that is the biggest difference.
So maybe it's a very good tool for teachers, not the students. Yeah, for in the classroom.
Yeah. I thought that too. Like just for the thing I did there in the front, working through this. I mean, if I had the system to do it, like I think it would make it easier to watch it. I wouldn't make any mistakes I don't want to do while I demonstrate this and so on. So that's one of the things. So I'm going out and talking to teachers and so on. I don't know why, like nobody really, like people are often like, wow, this is cool, like I want this, but when it comes to actually using it in the classroom, I think there's just like all these, like teachers are really, really busy. Like learning new technology, that's always difficult. So so one of the things we're actually doing right now is well, not having this as so I like in the beginning we kind of just went out there and say, look at this tool, you can just use this as your super powered whiteboard, do with it whatever you want. And like maybe we didn't meet the right teachers yet, but teachers seem to be like reluctant to just make this jump. So another thing we're doing right now is preparing like some problem sets which people can like assign as homework to their class. That way it might be an easier entrance to this because it doesn't take away from your classroom time. You kind of can just assign it to students, and if it doesn't work, it's not too bad.
So in terms of moving on, I assume you're familiar with the Mixed geometry sketchpad thing? geometry, in geometry sketchpad. That certainly was, I'm not sure it's still supported, but it was very, very well known for about 10 years.
Right, yeah, it was big, and then kind of this GeoGebra thing I showed,
Yeah.
they kind of like took over, and they're the big player in this area right now, and GeoGebra Sketchpad is kind of dying out a little bit.
I haven't tried it. What's it called?
GeoGebra.
Is G and then what algebra?
Geo, like
Geo, like a geometry.
Geo, and then Gebra. And one of the big differences that I can see is, I think actually Geometry Sketchpad might be on the technology side even be better or more advanced, I'm not sure. But one of the thing which like makes GeoGebra so popular is that it's like they have a different business model. It's free for all its users. It's free for teachers, free for school, free for the students. And they charge money if like somebody like Pearson comes and wants to include it in their material.
The nice thing that I remember about, there was a professor here, John Barwise, who died young, unfortunately. And he was not only a great logician, but also very interested in these kinds of tools. His stuff that was involved in essentially moving things around to show logical operations of geometry. He was a big fan of Sketchpad. And there are some interesting things in Sketchpad that you guys have never seen them. I do not know if geology does them. But there are things that appear to be theorems in the way that edges and triangles move, that are sort of Euclidean geometry theorems that are false. And there were very clever ways in Sketchpad to discover that the thing that you had almost convinced yourself was a true theorem was actually false. So it's very important kind of a way of using that tool to improve your appreciation of how subtle geometry is.
Interesting. Yeah, and I think a big part of this is actually this ability to be able to like play with it, quickly go through different constellations of this thing, like in a very intuitive way. Yeah.
Anyway, if there's something that GeoGebra or Geometry Sketchpad doesn't do that's like the philosophy that you're using here to kind of make everything under the user's control, that might be a direction to go someday.
Right. I mean, in a way, I think we're kind of doing something similar for algebra that they are doing for geometry. So I think these are actually two very like-minded approaches, and that might, and I think that might also mean that combining them
also,
is really powerful.
they didn't do three-dimensional analytic geometry. This is, of course, a smaller audience, so it's more the high school audience. Algebra is now taught earlier, but I always thought there was lots of stuff they could have done. I mean, I do some of this stuff in mathematics, I do in 3 and 4 dimensions, and there was stuff that you could have done in three-dimensional analytic geometry that was never really done.
And if you plan to extend your work in the geometry part, for example, the tool that I really needed in the classes was, for example, I wanted to student see if I change that parameter in the, for example, an ellipse equation, what happens in the shape of the ellipse. For example, in circle, in triangle, everything. Do you have any plan to have the geometry part? Because I what they saw, it was just algebra.
Right, so let me actually show you, I hope it's still open here somewhere. Oh yeah, so let's look at a circle here. So this is again GeoGebra, and it's like it can do a lot of things. So I can, oh, okay, I didn't mean to do that, but okay, there we go, we have another circle. And now I can move these things around, right? So now I can move this, and it updates everything and so on. And so this is a really cool system, and I definitely do not want to replicate the effort. Like my goal is just to use this and have these side by side. So, but about your question, so I actually do have this circle equation over here, and I can introduce it here. And now what I can do is I can go into this scrub mode maybe. Okay, it's just now that I want to demonstrate. It's not really working. But I mean, so I could, so if I change this here, I can at least change it here and see what changes over there. Like this is the one direction maybe you were talking about, and actually this is just not working in this demo I hacked together here. But you should be able to change these values here and observe what the changes in the geometry area.
It actually acts like a plugin for the GeoGebra and makes it more better.
Yeah, you could see it that way, exactly.
That's one of the really nice things we get from using JavaScript is that we just have all these listeners and it's really easy to just type into these. Whenever one thing happens in something, you can just wait for that thing to happen and then apply it to the other representation. Oh yeah. And so there's a lot of different areas that we want to expand to. One thing, we went to IUPUI recently as the entire lab, and they have this huge math tutoring center with literally thousands of students that use this. How many do they have per day?
Like several hundreds per day go through there, and they have big room, like bigger than this, with like all the walls are covered in like whiteboard paint. You can draw everywhere, and so they might bring like big displays in there soon too. So that's one cool thing I think, to actually like have this canvas replace this whiteboard. What that does, certainly you'll have to make sort of adjustments to the UI. Like you don't here to press the buttons, for example, or like you could like actually with some people we work with some people in Booster from WPI, and so they have this homework assignment tool, and actually they find that a lot of students use their smartphone to do. So it's the other extreme, right? Can this kind of thing interaction work on a screen which is so small? I personally always like have my finger right on top of the thing which I want to see, but maybe with some smart changes this could work out. So basically, maybe to wrap this up, because I'm sure people need to leave soon. Thank you for coming here. This was really fun for me. Hope it was fun for you too. And so so we're looking for people to collaborate together on this, maybe research-wise. We're also looking for people who want to join the team and help developing this. And also, if you have any ideas about this, you just might want to talk to us.
Even if you don't join on with the development of GM, like the data that we generate is so there's a lot of the reason that I originally got into this is because when I was using the online homework systems and everything, most of these systems or most digital systems that have to do with students solving math problems involve them giving you the problem, and then you have one little answer box. You do it all on paper and you write your answer in. That doesn't tell you anything about the intermediary steps took. So this is really one of the only systems, I think, where we actually have data that shows very fine-grained actions that students took, and you can infer a decent amount of reasoning about that, about the transitions between the different expressions. And so when we make this data available, which we're currently in the process of giving people a web portal access to this data, I mean, this data is just, it's good data. As Donald Trump would say, we have the best data. So once we have that open, then for anyone who's interested in anything related to how do students think about math in a cognitive sense, this really is one of the best. You could just give them some problems that you want them to solve, however many students you want them to solve it, get that data, and then get it in CV or JSON format, and then do whatever analysis